Hello everybody, welcome into another lesson. So today we are going to be given equations of conic sections, and from the start we're not going to know which type of conic section it is. But now that we've gone through the four various types of conic sections, we've gone through the circle, the parabola, the ellipse, and the hyperbola. So we should now be comfortable with graphing these and also simplifying these equations and finding all the information about these conic sections. Well, in standard form, you have the standard form of an equation of a conic section is ax squared plus bxy plus cy squared plus dx plus ey plus f equals 0. And notice you probably see that xy term. We haven't had that up to this point, and we're not going to have that in today's lesson, but that actually ties into the next lesson when we talk about rotation of axes, and we'll get into that in the next lesson. We won't actually have a b term today or an xy term today, but this is the general form for the standard equation of a conic section. We'll have all others, just not the b term, but there is a very quick way to tell what type of conic section you're actually dealing with. If the coefficient on your x squared and y squared term are equal, so the a equals c, then you have a circle. Which makes sense because in a conic section, when you've had them equal to each other, you've always had a circle. You could think of it as an ellipse with equal axes lengths where both the x and y axis are the major axes, so they're equal. A circle is basically a perfectly equal ellipse on both axes. But if a equals c, you have a circle. Now, this is provided neither a nor c equals 0. Because if either one of them equals 0, what you actually have then is a parabola. If a times c, the coefficient on the x squared times the coefficient on the y squared equals 0, you have a parabola. And this reiterates the point that both of them together can't equal 0. Well, basically, I probably don't want to say a plus c can't equal 0 the more I think of that. It should be more a or c can be 0, but not both. That's probably the best way to write this. So a or c can be 0, but not both, which that also makes sense because in a parabola, only one of the variables is quadratic. If you had a coefficient of 0, you're only going to be left with one of the terms quadratic. If they were both 0, then you're just either going to have a rational function or a linear function. So you wouldn't even have a normal conic section at that point. Well, rational functions technically do produce hyperbolas, but they're different than the type we've been dealing with. But we're not going to go that deep today. And then if you have the product of your x squared times your y squared coefficients greater than 0, you have an ellipse. That's if they have like signs, like if both a and c are positive, or if they're both negative, you get a positive answer when you multiply them, you have an ellipse. And then if a times c, or the coefficient on your x squared times the coefficient on your y squared is less than 0, you have a hyperbola. That would of course occur if the coefficient on the x squared was positive and the coefficient on the y squared was negative, or vice versa. That's when you would have a hyperbola. And what was I going to say? I was going to say something along the lines of the coefficients about, oh yeah, that makes sense with the hyperbola because usually you have for hyperbola, one of the quadratics has a positive term, the other quadratic has a negative term. So that really ties in with what we've been talking about. So we're going to do 6 equations here and we're going to classify them. So let's start with the first one. So I have 9x squared plus 4y squared plus, actually minus, excuse me, minus 18x plus 16y minus 119 equals 0. Alright, so I have been given 9x squared plus 4y squared minus 18x plus 16y minus 119 equals 0. We want to first establish what type of conic section is this. Well, notice the coefficient on my x squared is 9, and then the coefficient on my y squared is 4. If I take those and multiply them, I'll get a value of 36, which is greater than 0. If the coefficient on my x squared and y squared term multiplied together is greater than 0, you have an ellipse. So that's part 1 of the question. This is an ellipse. Having said that, we need to identify everything about it. In order to do that, we need to get this into standard form. So let's go ahead and start working on that here. So let's get the x and y terms together, get the constant term out of the left-hand side. So this would turn into 9x squared minus 18x plus 4y squared plus 16y is equal to 119. Alright, so again now, what do we know about the quadratic coefficients? Ultimately, they need to have a coefficient of 1, so with the x terms, I can factor out a common 9, giving me 9 times x squared minus 2x, plus, with the y's, I can factor out a common 4, so 4 times y squared plus 4y is equal to 119. Now, what I need to do is complete the square with both of these quantities. So I'll have 9 times, alright, so x squared minus 2x, half of negative 2 is negative 1. If I square that, I get positive 1. Plus, I'll take 4 times, alright, so I'll have y squared plus 4y. Half of 4 is 2. If I square that, I get 4. But what you do to one side, you gotta do to the other. So I'll have 119 plus 9 times that 1, that's 9, plus 4 times that 4, which is 16. So this would simplify into 9 times the quantity of x minus 1 squared plus 4 times y plus 2 squared is equal to 144. Well, what do we know about an ellipse? The right-hand side has to equal 1 to be in standard form, so I have to go through and divide everything by 144. This would give me x minus 1 squared over 16 plus y plus 2 squared over 36 is equal to 1. Now I have this equation of the ellipse in standard form. Well, it looks like the number below the y, the denominator below the y, is bigger, so the y-axis is the major axis, which means then that the x-axis is the minor axis. Alright, so let's find the center. Well, that's going to be x minus 1 equals 0, the x coordinate would be 1. Then the y plus 2 equals 0, the y coordinate would be negative 2. So the center of this ellipse would be at 1, negative 2. Now, let's see. We can take a squared, of course, equals 36, which means a has to equal both plus and minus 6. B squared equals 16, which means b has to equal plus and minus 4. So now I can find my vertices. Let's start with the major axis first, being the y-axis. That means I'll leave my y-coordinate alone. So if I take 6 and subtract that from negative 2, I'll have negative 8. So my first vertex, yeah, we'll call it the vertex there. My vertices then are, let's see, we'll have 1, negative 8. And then we'll have, if I take negative 2 plus 6, that'll give me another point of 1, positive 4. Now we need to deal with the minor axis. So this time, x-axis is the minor axis. If I take 1 minus that 4, I would get negative 3 and leave my y-coordinate of negative 2 alone. So I'll have negative 3, negative 2. Then if I take 1 plus 4, I would end up getting 5. So I'll have a coordinate of 5, negative 2. So there's my 4 vertices. Now I have already enough to graph this. But last but not least, we actually need to find the foci. The foci of an ellipse is going to be given as c squared equals a squared minus b squared, which in this case is going to be 36 minus 16, which equals 20. So c is going to equal that square root of 20, which is the 4 times the square root of 5, so that'd be plus and minus 2 times the square root of 5. And then, of course, the foci are always affected on the major axis. In this case, that's the y-axis. So I'll leave the x-coordinate of the center alone of 1. Then I'll take that negative 2 and do both plus and minus 2 times the square root of 5. Those would be my foci for the ellipse here. So I first identified this equation as an ellipse, then I simplified it and got it into standard form, and then I was able to give all that information, and we have enough to graph it if we chose to, but we're not going to today. Alright, let's move on to another one here. Alright, next. X squared plus y squared minus 4x minus 6y minus 23 equals 0. So we have x squared plus y squared minus 4x minus 6y minus 23 equals 0. Well, we can see the coefficient on the x squared equals the coefficient on the y squared, so 1 equals 1. This means we actually have a circle. So this particular conic section is going to be a circle. Now, of course, we want to simplify this to get this into standard form, so we need to get our x and y terms together on the left-hand side and get the negative 23 out of the left-hand side. So this will start out as x squared minus 4x plus y squared minus 6y equals 23. Now we just need to complete the squares for the x and the y, so this would turn into x squared minus 4x. Half of negative 4 is negative 2. You square that, you'll get plus 4. Plus you got y squared minus 6y. Half of negative 6 is negative 3. You square that, you get positive 9. So on the right hand side, you'd have 23 plus 4 plus 9. So this would simplify into x minus 2 quantity squared plus y minus 3 quantity squared is equal to 23 plus 4 is 27 plus 9 is 36. Alright, so with the circle, we need to, of course, identify the center of the circle. The center, so take x minus 2, set it equal to 0. The x coordinate is 2. Y minus 3 equals 0. The y coordinate is 3. So the center of this particular circle can be found at 2, 3. The right-hand side's always the radius squared. We know the radius squared, here, let me circle the center. Radius squared equals 36. That means then that the radius equals 6. So we have a radius of 6 on the circle. Now we just need to find 4 different endpoints on the circle. And usually you're going to do that by taking your radius, adding and subtracting that from both the x and the y coordinates. So we should get 4 endpoints. So endpoints. So if I take 2 minus 6, I should then get negative 4, 3. If I take 2 plus 6, I should end up getting 8, 3. And then if I leave my x coordinate alone this time of 2, if I take 3 minus 6, I should get negative 3. Then if I leave my x coordinate alone again, I take 3 plus 6, I should get 9. So I have 4 endpoints located at negative 4, 3, 8, 3, 2, negative 3, and 2, 9. So that was everything I needed to know about the circle, and I have enough to graph this if I so chose to. Alright, let's go on to another one. Good one. Alright. 16x squared minus 9y squared plus 32x plus 54y minus 209 equals 0. Alright, so what a bit of a mess we have here. So we have 16x squared minus 9y squared plus 32x plus 54y minus 209 equals 0. Well, first, what type of conic section is this? Look at my coefficient on the x and x squared and the coefficient on the y squared. So if I take 16 times negative 9, that's going to give me negative 144, which is less than 0. Since that's less than 0, we have a hyperbola. So we are actually about to end up with a hyperbola for this conic section. Alright, so again, we need to start to work to get this into standard form. So get your x and y terms together on one side and get the constant term out of the left-hand side. This would turn into 16x squared plus 32x minus 9y squared plus 54y is equal to 209. Alright, well again, the coefficients on the quadratic terms need to be a positive 1, so from the x's I can factor out a common 16, which would be 16 then times x squared plus 2x, And then with the y's, I can factor out a negative 9, so this would be minus 9 times y squared minus 6y. All that equals 209. Alright, now I just need to complete the square for each of these quantities, so I'll have 16 times x squared plus 2x. Half of 2 is 1, 1 squared is 1. And then I'll end up having minus 9 times, in my parentheses, I'll have y squared minus 6y. Half of negative 6 is negative 3. If I square that, I get plus 9. That would equal 209. So this would simplify into 16 times the quantity of x plus 1 squared minus 9 times y minus 3 squared. Well, actually, I forgot to do the completing the square on the right-hand side. 16 times 1, I'll add 16. Then minus 9 times 9, that'd be minus 81. So the right-hand side, so 225 minus 81 is 144. There we go. Now, of course, for a hyperbola, the right-hand side has to equal 1, so I got to divide everything by 144. This would give me x plus 1 squared over 9 minus the quantity of y minus 3 squared over 16 equals 1. Now I got the equation of the hyperbola in standard form. So let's start with what axis it has symmetry with. Well, the axis to the left of the minus sign, so this is going to be x-axis symmetry. So we've established the x-axis symmetry. Now, what's the center of this? So the center, if I set the x plus 1 equal to 0, that's going to then give me x equals negative 1 for my x-coordinate. If I set y minus 3 equal to 0, that gives me a y-coordinate of 3. So the center of this hyperbola is going to be found at negative 1, 3. Okay, a few things left to do. So what we need to do is first, I'm going to say we find the vertices. Well, what do we know? We know a squared equals 9, which means a equals plus and minus 3. So we have that. Now we're going to, since the x-axis is the one with the symmetry, we're going to take that plus and minus 3 and affect our x-coordinates of the center. So for our vertices, if I take negative 1 minus 3, I'd have negative 4. Then, of course, I leave my y-coordinate of 3 alone. And then if I take negative 1 plus 3, I would have positive 2, and then my y-coordinate of 3. So those are my vertices, would be at negative 4, 3, and then 2, 3. See, I need to find foci and asymptotes. Now, to find the foci of a hyperbola, it's actually c squared equals a squared plus b squared. An ellipse was c squared equals a squared minus b squared. A hyperbola is c squared equals a squared plus b squared. You could think of it as the opposite of what the sign is for the hyperbola. The hyperbola in standard form, you have a minus, so the focus has to be a plus. In an ellipse, you have a plus, so you have to have a minus for the foci equation. So in this case, a squared was 9 plus the b squared of 16, which gives me 25. So c would equal plus and minus 5. Now the foci always again deal with your axis of symmetry. So we should have two foci, kind of like you would on in an ellipse or in a parabola. So the foci, if I affect my x-coordinate. I take -1 minus 5, I'd end up getting -6, but leave my y-coordinate of 3 alone. And then if I take -1 plus 5, I would end up getting 4, and then leave my y-coordinate of 3 alone. So my foci of this hyperbola would be at -6, 3, and then 4, 3. And then we need to find asymptotes. So we ignore the 1, remember that, we ignore the 1, we set one variable equal to the other, so you would end up having y minus 3 quantity squared over 16 equals that x plus 1 quantity squared over 9. Well, this would turn into y minus 3 squared equals 16/9 times the quantity of x plus 1 squared, because remember, the ultimate goal is to solve for y and get two equations of asymptotes, which will help guide the shape of the hyperbola. So this would turn into y minus 3 equals plus and minus 4/3 times x plus 1. That's the native form. Let's go with the positive 4/3 first. So y minus 3 equals 4/3 times x plus 1. That would be, well, 4/3 x plus 4/3. So then we'll have y equals 4/3 x. So 4/3 plus 3 is the same as 4/3 plus 4/3 plus 9/3. That would give me 13/3. So the first asymptote would be at y equals 4/3 x plus 13/3. I still have a second asymptote. So y minus 3 then, if I take -4/3, so I'd end up getting -4/3 x minus 4/3. That would give me my final asymptote at y equals -4/3 x. -4/3 plus 9/3, that'd be plus 5/3. So my second asymptote for this hyperbola would be y equals -4/3 x plus 5/3. So yes, hyperbolas have a lot going on. But given the original equation, identifying it as a hyperbola, getting the equation of that hyperbola into standard form, we could identify all this information and get a graph of it. I got 3 more. You know what? I think I'll do one more. I think an example of each is enough. I think one of each is enough, because these can get quite lengthy. Especially if you're given a hyperbola. We see how lengthy that was. Good one. So we have y squared plus 12x plus 4y plus 28 equals 0. So we just have y squared plus 12x plus 4y plus 28 equals 0. Well, you have no x squared coefficient, but the coefficient on y squared is 1, so if I take 0 times 1, I just get 0, which means this is a parabola. So in this case, we are going to have a parabola for this conic section. Now, in a parabola, the quadratic variable is on the left, the linear is on the right. So we need to get the linear term, the linear variable rather, and the constant term moved over to the right-hand side. So this is going to simplify into y squared plus 4y is equal to -12x minus 28. Well, we should ultimately get y plus some quantity squared over here, which means we're going to have to complete the square on the left-hand side. So this will become y squared plus 4y. Now half of 4 is 2. If you square 2, you get 4. So this would be plus 4. That would equal negative 12x minus 28 plus 4. Left-hand side simplifies into y plus 2 quantity squared equals negative 12x minus 24. Now, the linear variable even needs to have a coefficient of 1, so we need to factor out a common negative 12 on the right. This would be y plus 2 quantity squared equals negative 12 times x plus 2. Now we have the equation of this parabola in standard form. So what axis of symmetry does this have? Remember, with a parabola, it's always the linear variable that dictates the axis of symmetry. So this has x-axis symmetry. So we will have x-axis symmetry for this parabola. Now, next thing is find the vertex. Well, the vertex of this parabola, set x plus 2 equal to 0, you'll get the x coordinate at negative 2. Set the y plus 2 equal to 0, you'll also get the y coordinate at negative 2. So you have a vertex at negative 2, negative 2. So this parabola should open to the left, but we didn't ask for that. But now, what do we remember about the coefficient on the linear quantity? It's actually 4p equals that coefficient. So 4p is going to equal that negative 12, which means p equals negative 3. Alright, that's great. We found the p, so what do we do with it? Well, we need to find a couple things still. The focus, remember, to find the focus, you're going to take that p and add it to the coordinate of the axis of symmetry. Since it's x-axis symmetry, we'll take that p of negative 3, add it to the x coordinate of the vertex. So negative 2 plus negative 3 is negative 5. And then we'd have the y coordinates left alone. So the focus of this parabola is at negative 5, negative 2. Last but not least, for parabolas, we have a directrix. To find the directrix, that's based on the axis of symmetry. That's going to be a dead giveaway for the directrix. If it's x-axis symmetry, it'll be in the form of x equals. Then I'll take the negative 3 and subtract that from the x coordinate of my vertex. So negative 2 minus negative 3 turns into negative 2 plus 3, which would be 1. So I would have a directrix for this parabola at x equals 1. So I was able again to identify this equation as a parabola, get it into standard form, and get all the information we need to compile a graph if we were asked to do that. So that's it for this lesson. Next lesson is going to be very interesting, because in these conic sections equations we'll have an xy term, which really represents how the xy axis was rotated. The xy plane's been rotated, and you're going to have some off-center conic sections. And the idea of that lesson will be how many degrees do we need to rotate that axis to get it back to normal and eliminate the xy term. So that's going to be an interesting lesson. So I hope everybody has a great day. Take care.